So, as I said, big data and machine learning for customer returns is the topic Rahima Mohammed is going to cover from Intel. Rahima is a senior principal engineer currently leading the data automation infrastructure of performance and power and workload sensing office of the IP Competitive Analytics, IPCA, at Intel. Prior to IPCA, she served as a data center customer solutions technologist, in which she led a data mining effort on customer return parts. Over her greater than 22 years of tenure at Intel, she has chaired various technical steering committees, serves as a reviewer in premier international and internal and external conferences, and serves on industry advisory boards. She demonstrates consistent leadership in IP creation and has published more than 140 papers in Intel internal and external conferences and filed 8 patents. She is a diversity champion, winner of the 2015 Society of Women Engineers Prism Award, and winner of the 2020 Society of Women Engineers Advocate for Women in Engineering Award. With that, I hand it off to Rahima to talk about big data and machine learning. Thank you, Rahima.
Thank you. Thank you, Ramana. That's a kind introduction. And thanks to all of you for joining this presentation. Good morning, good afternoon, and good evening to each one of you. Thank you for joining this presentation. And this presentation is actually on big data and machine learning for customer returns. So actually both Ira and John did a wonderful job of talking about how the market is looking and how the market is shaping. Actually, I'm going to be talking a little bit about, as these technologies are progressing, how the specifics of the defects are coming, and which leads to the customer returns. And that's the topic of today. And so with that introduction, let me explain to you what I'll be actually going over, kind of explain to you the problem and what we are proposing, the methodology, results, and conclusions. But more importantly, as I go through this content, I'd also like to make sure this is only touching kind of the beginning of the issues, but there's a lot of extra now work that's going on, which can do this type of work, as well as the amount of technology that we should be bringing up for this type of a problem is pretty intense, and we should be thinking about. So with that introduction, I'll jump into what's the problem statement. So the question is, with all the excitement about the growth of the semiconductor industry, and since I'm from Intel, that's what we work on all the time, and it's exciting. But as the question is, where is the defects coming from? So with that introduction, I want to really focus on, in the last 22 years, I think we've been going through the various process changes. And as you can tell that, moving from 3 big shifts that we have had was on the strained silicon at 90 nanometer, high-K metal gate at 45 nanometers. And then we started with the 3D transistors, the 22 nanometer. And interestingly enough, at each and every process generation, of course, there's a lot of hiccups and there's a lot of things we have to push on. But these latest ones, the 14 nanometer and 10 nanometer, surely is pushing us quite a bit on trying to make sure we understand the details of the defects, just because of how the number of defects are actually increasing. So at every generation, what we are trying to do is, you are trying to execute a Moore's law. You're enabling new devices, adding more, packing more and more devices. And each and every device that you're adding, you're trying to bring in a higher functionality and complexity. But you're also at the same time trying to keep the power cost and the size and maybe even the throughput time much smaller. So with all of that comes the challenges of the test and manufacturing and the test environment, where you're trying to also get to the market in the time, and how much cost is it going to be. So with all that comes the challenges of how you're increasing the number of defects as you're decreasing in the process generation. With each manufacturing process generation, as you're decreasing in the wavelength, the number of manufacturing defects actually increases. So that's the reason why understanding this and kind of characterizing the defective units is very critical to improve the quality of the products delivered to the market. So for every generation, I think the other important thing is that the quality of the product is also connected to the brand of the silicon. And the brand name is super critical because that is where, if the end user experience is not good or they're running into difficulties, that's why understanding the defects is so critical. So the next question I'd like to also bring up is that, one of the other things that I have spent a lot of time, because as a customer solutions technologist, is kind of trying to also understand defects from a process perspective, but also defects from understanding what we are testing. So as we go through these processes, one of the other things is understanding the markets. And so John's presentation was really good because, it talked a lot about the growth as well as the different markets, and so was Ira's. So one of the interesting examples is what type of content are you running and what type of issues are you facing? So from that perspective, it's like understanding the market, understanding the workloads, understanding what the customer is doing is super critical because are your tests connected to that? So the next thing is for us to trying to understand what is actually going on. So here I just have a cartoon of kind of the processes that's going on. So, and then here we are looking for the defective units. Remember, we are trying to figure out what makes a part fail. So if you look at the manufacturing processes that we have, we go through the fab wafer process. And if you see the kind of work I'm presenting and the reason why I drew the fab wafer process and electrical test in a different background is because I'm actually talking about all the data connected in the white part, not actually on the fab wafer process or the electrical test part. So once the part is electrically tested, then comes the next step, which is it goes through the sort at the cold and at the hot. Then it goes through the die level cherry picking, goes through the assembly process. It goes through a huge burn-in, and John already answered a lot of good questions on the burn-in. Then it goes through the class test. This is where quite a bit of interesting things are happening. Class test is where you're binning, you're refusing, you're doing the class test, binning, fusing, all of that is happening at class. Then comes the system level validation. So as a customer solutions technologist, when you get a return, you never get a return and you will figure out where the problem actually happened. Most of the time, we are trying to figure out what actually is failing first through the system level validation because the customer is using and that mimics the customer environment the best possible. And then you go through the quality assurance. You can also have problems is you do the packaging, and that's the whole path is being traced. And the work I'm talking about is trying to look into all the data that's actually starting from a visual ID of the part. How do you actually connect all the data from all the way from sort to the end, which is all the way to the package? So in a common environment, what you're doing is in the traditional commonality analysis, each one of us, we know by engineering judgment, let's look into this, let's look into different things, but most of the cases you are using variables and statistical methods, mostly from that particular process, not from the specifics of kind of the interactions that is going on between the things, between each of the steps and the processes. So in the traditional analysis, we're doing quite a bit of correlations and regression analysis at each and every step of the process. What we are talking about, and if you do this traditional analysis in the common ways that we're talking about, that actually leads forced commonalities, and you really avoid understanding the interactions between the processes. And since these returns from the customers are actually pretty difficult to find, and it's like finding a needle in a haystack, just because it could be coming from so many different sources. So that's the purpose of why we're coming up with this new methodology, where what you're actually doing is going through a few other steps trying to use big data, but that's the what are the difficulties. Now, in order for us to take the data at each and every step of the process, that's what I'm calling as the data extraction. And this is where you are looking into the unique processor ID, and from the processor ID, you're trying to recreate the history. And when I talk about recreating the history, what I'm thinking about is actually each and every part got tested at sort, remember, sort, the DLCP, burn-in, class, and binning, the fusing. Binning and fusing happens right after class, and then comes the system level validation, then goes through the QA parts. You are trying to bring in the data from each and every step of the whole manufacturing process. And I'll go over the details of how we are doing the neighboring parts and repeating the history creation, because it's the neighboring parts that causes some of the reasons why the data grows so much. And then how do you take so much for each of these parts, each of the processor ID that you've created? How do you take that and go through all these different steps of the process? And then once you have extracted this, now I need to analyze it. And here, what we are doing is, at least in this methodology, what we created is using machine learning methods to actually find the most critical parameters. And I'll go through this. This is called the feature selection process. So you will see that what we are doing and for selecting the variables. And then we are using supervised segmentation analysis to narrow down thousands of variables to a few relevant ones. And when I say a few relevant ones, you'll be playing with the number of relevant ones too, quite a bit, just trying to make sure which one makes more sense. Once you look at these variables and the segmentation analysis, in order to really visualize this, that's where you need the multivariate graphical analysis to find these patterns. And the data visualization, the kind of visualizations, the kind of details becomes quite very critical for us to kind of look into this. And then once you find this specific patterns, that's when you're trying to actually look at this. Okay, I found a pattern. I understand that there is something. Then comes the next part is like, how does this translate to test issues and potential causal mechanisms for these defective parts, just so that you can actually go ahead and make a change in the process so that the next time onwards, these issues will not happen. So with that, by the way, I did forget to mention that please do keep submitting questions, and I can stop anytime to answer your questions, because I do want to keep this session very interactive. And as you have questions, please do stop me. So Ramana, I'm open for questions anytime. So with that, so just to go over the methodology, we extracted the data, analyzed the data, visualized it, and then trying to come up with a causal mechanism so that we can make an actual change to the test environment. Now, following this, so this is kind of where I'm trying to figure out, okay, I have customer returns, and how does this customer returns lead to big data? So remember, I have my wafer, and you got a part. And in this case, the part is just a unique processor ID. That part has all these neighbors. And so in this case, we're just kind of trying to follow up who are the neighbors and what happened to it. So remember, from the unique processor ID, I'm trying to go back into wafer level sort, package level data. In the package level, you're looking at burn-in, class, binning, fusing, system level validation, QA, and packaging they work. Now, the whole purpose behind this is because you're trying to trace the neighboring parts. And when I'm trying to trace the neighboring parts, I'm trying to think about same lot and same test program. Why? Because each part, every 2 weeks, we have a cadence. This is just discussion. This is a cadence of 2 weeks. As the part is maturing, every 2 weeks, the test programs get updated. So if you don't have a pinning mechanism, the whole the life of the silicon as you're going through the process, it's quite long. So one of the key indicators that I'm using is the unique ID and which lots did it come from and the same test program. And then I also picked on neighboring lots and wafers because the issue could be coming directly from just one of the place, maybe an equipment, maybe whatever the details are. That's the reason for also picking the neighboring lots and wafers. And Intel does have many manufacturing sites. And at the time I was working on this, I was working with 11 sites. So same condition at each of the manufacturing tests at the various manufacturing sites. So you want to be taking a look at that. Is this also coming mainly from a particular site, or is this coming because overall the test parameters are changing in a way that that's causing the problem? So with these pinning mechanisms, that's why you're just seeing that I'm taking a data from the same lot, same test program, neighboring lots on the wafers, but you're also very carefully looking at the conditions. And then from there, what's happening is, just for an example, if I picked 3 parts, just 3 tests, sort, class, and system level validation, there itself, you can go ahead and get somewhere close to 78,000 parameters. And all the variables you're taking a look at are parametric data and attribute data. The parametric data example is like your leakage, voltage, process monitors. Attribute data are your product characteristics, die position on the wafer, lot numbers, etc. So that's why this thing grows quite a bit. And that's why for any single part, if you got, you are going somewhere between 19 to 78,000 variables for only 3 of these tests. And we don't have 3 tests. So that's why the data grows so much.
So Rahima, a related question to that is, what is the minimum data set size you would think is required to get a good result from or information from this method?
We could get, we don't need to have very large. I was even working with 1,600 data sets. But you can handle much, much bigger. Okay. So lower is not the problem. Higher is the problem. Because you have to handle the things very actively. Okay, so with that, then the next thing is now we understand why it leads to big data. But the big data part also, the data is very, has various types. Now that comes the discussions. The big data that you're coming up with is kind of an interesting problem. The different constituents that you have is quite a bit, and on each of the 4 vectors of, I think if you call the 4 V's, on both the 4 V's have the volume, variety, velocity, and the veracity. Let me explain each one of them because that'll help us to think. Each one of us, when we are working with test environment, these are some of our common problems. That the sheer volume of the data of the process that I just explained, that leads to the data. But the variety is very interesting. Variety is, this is where, remember, the data that you're getting is all the way from sort to the packaging, but also the way you get the data from the customers. I can tell you that just because of the amount of work I've worked with the customers, one of the interesting things is returns from the customers. Sometimes the only thing you can understand is that it doesn't work. And many of our customers do not have neither the patience nor, I can understand why, but at the same time, neither the patience nor the discipline to tell you exactly what the issue is or where the issue may be coming from. So sometimes they're just very discrete data. It's like a part failing, blue screen of death, part, maybe um, just kind of machine errors. And some of them will tell you then, no, these are not machine errors, but these are just kind of glitchy errors, etc. So you're going to get kind of very incomplete data sets from the customer aspects. And that is the reason why, as soon as you start getting the part, really pinpointing the problem is very difficult. That's the reason why we're trying to go back to all these different steps in the process to kind of study what went wrong in our side. And it could be structured data, that's the categorical and continuous. By the way, all of you know that as you're working through this manufacturing process, the other big aspects of the part or the data sometimes you're using is trying to understand the semi-structured data, which actually comes from many of the manufacturing tests, and then sometimes from our partner organization, the validation part, where you're also trying to understand in a power and performance situation or in a specific functional situation, how is this behaving? So that's a textual data. And you are just trying to get an understanding of it's a category of the data, but it's very textual. And then comes a non-structured data, which is a part is failing. And you are taking a look at under the microscope, and you're really taking a look at kind of also at a cross-section, the SEM characteristics. So many of that data is actually all video, audio, textual data. And in certain cases, the audio stuff comes especially from certain cases where your audio quality is it's not good. And then you're trying to figure out what combination is causing the problem. So, and the data complexity in many cases, some of this data is coded. So then there's a lot of decoding and transformations that you have to go through to actually look at the data, just because of the whole manufacturing process is extremely complicated. So then the last one is probably a discipline issue. And it's each of these data lies in different databases. And the databases don't talk to each other. The retention of the data is a very complex problem because the data grows very fast. So if the customer return came to you something like a year and a half old data, that's it, the data is not there. So we are always trying to figure out how to archive the data and how to retrieve the data from the different archives, and the process again is not very easy. And the velocity is super critical, because this is where, when a customer comes up with issues, you're always trying to figure out, how fast can you give that data? Can you come back with a response saying, should we try this, or these are the possibilities, that's the reason we should make this change to make this happen. So that's how fast you want this. The veracity of the data is very interesting. The uncertainty in the data can come from the customer part. The uncertainty in the data can also come from our area. And why do I say that? And that's just because there is a lot of incompleteness or sometimes missing data. And I'll give you an example. I was blown away, like many a times when I saw missed data. And I found two sources which causes very big issues. Sometimes many of them are because actually there were network failures. And the other cases which I found was blew my mind, and I even went all the way to the top of the manufacturing line manager to make sure that that doesn't happen. Is every week you have a budget to give, and you have to deliver these many parts. So by the weekend, and what you will observe, and I have beautiful data sets to show you guys that, it's like by the weekend, some part of the data is missing. And that's usually always, they're in such a pressure, they will at times, the check processes, the steps and steps for all the checks that you should do at times doesn't get done. And that's the part that you'll have some of this missing data. Some of the data will be there. They will be so ambiguous. I have no way of understanding the data. So that's the ambiguities and the latency and kind of all the approximations that goes into. So the big data constituents are very huge in the manufacturing data. I think those of us working in this field can work for another 15, 20 years and still be getting so excited about this work.
So Rahima, I have a couple of questions that I think are relevant to the slide you just showed.
Yeah, sure,
right?
sure.
And I'm going to try and merge them together, right? So first question really is with the velocity, right? How often, does this data cause you to revise the test? If very frequent test changes are made, how can you mask reliability issues? You may be masking reliability issues due to changing test methods, and do you change that test real time? And I think the second question was, do you see any data that supports the fact that these are all time zero failures, right? And not something that is reliability at the customer.
Okay, so both are very good questions. So the first one is, that's a good question that, if you make this, if the causal mechanisms are going to continuously change the data, right? With the system setup that we have, I don't think you can change the data real time. You can give the feedback to the customers real time, but in order to implement the changes, it's a two-week cadence. But you cannot get to a 2-week cadence unless you prove out the process. So I would say things will not happen unless you go through the proving out the process, which is somewhere between 2 to 4 weeks, and then 2 weeks to implement this. So that's the cadence that we have right now. Now, as things become, sorry, Ramana, you had a second question for me. Tell me, what was that?
It was the assumption in the process is that these are all time zero failures, right? So how does your data kind of support that?
That's a good question. So that's a very good question. So I think in this case, the type of the work we are talking about is related to time zero failures, but there is a lot of other things that we have with the reliability aspects of it. Some of the special type of issues that are coming back from the customers is actually not related to the time zero failure. And that's the other interesting part that, if you go through, we have also done some cases where we exercise some of the parts and see if we can reproduce the same issues that the customers are seeing. So certain times it is a reliability issue, but in many of the problems that I'm talking about, these are time zero issues. Is that clear?
Yes. And I think we can wait till the end now for these two questions to be answered, but
go ahead.
Are the subcontractors and silicon foundries and assembly houses as a part of this data set? What is your experience with them? And also,
let me answer that. So that's a very good question. The data that I have been showing and the whole system that we have set up right now doesn't include the, for example, if I'm working with other parties, either TSMC or Samsung, or for that matter, any of the OSATs, then it doesn't include. It's everything here is our internal data. But we have had a few cases where we needed in collaboration between Intel and TSMC. In those cases, and this whole process does not include TSMC data.
And what is the size of a typical data set stored in your database for an average device, and how does it grow over time?
It grows very badly. So for an example, I was talking about one part can be something around 78,000 variables. So you're looking at petabytes of data, and sometimes the smaller ones are not as big, but I think also depends on how many returns you're getting from the customer. So if your number of variables keeps increasing, that's another part of the data that you have. The growth in the data set is the main problem why you have this different databases, and you also have the difficulty of the retention. The data, if you ask me, one of the examples that at least I tell our execs is very much like we need to solve some of the toughest problems related to the related to how we move into 3 nanometer, 5 nanometer discussions. But managing data management overall is also extremely complex and has to be done very well. Okay, so the data mining goals that we have is the, Ramana, may I move, or do you have any other questions?
No, please go ahead.
Okay, so the data mining goals for us here is actually, the main idea behind this is, as I mentioned, it's finding a needle in the haystack. That's the difficulty of the problem. And finding hidden patterns to explain differences between defective and non-defective parts. So you have to kind of truly care and understand what is a defective part and a non-defective part. So I'm making some assumptions. Let me explain those. So I'm making the assumption that the returned parts are defective parts. And the ones that we have sent out to the customers, or the ones that are there and that haven't come back, are the non-defective parts. So that's the assumption that is there in this. And what we're doing is trying to take this and come up with a process of selecting a subset of these features. And that's the feature selection or variable selection methodology. And the main goal behind this is to reduce the variance and avoid the overfitting. And imagine this is kind of sorry, I need to come up with the laser pointer again. Okay, so this is the M is your number of variables for each, and N is the number of rows. And this is related to your, for example, each part ID, unique processor ID is your rows, and your M is the variables corresponding to each of the parts. So what you're trying to do is, if I have 100,000 variables here, how do I bring it to an M prime, M to an M prime, which is based on this reducing the variance, avoiding the overfitting. And that's what is happening through this process of feature selection. And this helps us to reduce from hundreds and thousands of variables to the most meaningful ones, trying to connect each one of them. Once that's done, then you've selected the features, selected what is important, and then from there, we are trying to go ahead and find these data mining mechanisms, which is where you use these decision trees. And I'm going to talk about the 3 that we have used, and actually there are probably a ton more that we could have used, but these are the top 3 that we found very useful. And the first one is the classification and regression tree, the CART. And then the second one is the random forest. And the third one was the gradient boosting tree. Each one of them shows a nice picture, which is, for example, it shows you kind of like each and every thing is considered binary. You understand, find 2 things. One is 0 is the defective, one is the non-defective. And considering this, you're just basically partitioning one after another and trying to understand which path gives you a nice understanding. The random forest, you're basically looking at multiple rows and variables at the same time. In the gradient boosting tree, basically, you're looking at multiple trees at the same time and trying to look at the predictions from them. So on the classification and regression tree, this is a simple learning tool that you can do in recursive partitioning, and you're using binary recursive partitioning algorithm to kind of hone in on where could the problems be. The second one is the case when you have a lot of the number of variables, number of returns, or the number of unique processor IDs a huge lot larger than the number of observations. Observations means the number of variables that you're going to be studying. So this comes out, random forest is a pretty nice, very fast methodology in the cases where you have a huge number of variables. The gradient boosting tree, on the other hand, is if you have a large number of observations, large number of variables to study, but you don't have as many parts or unique processor IDs to worry about. This might get slow, especially if the variables are huge, but otherwise it's a very nice mechanism for us to study. And we did this three and in a careful way. And you can see what we did was this. How do I get rid of this? Okay. The dynamic, in this case, you really want to be able to also visualize this. Once you have done the feature selection, then you have gone through the decision tree algorithms, then I really need a dynamic graphical user interface for us to study this carefully. And you can see the 4 that we are using. And this actually, we have come up with a tool called Interactive Data Exploration and Learning Tool with these 3 decision trees and feature selection methodology. And the 4 major graphical user interfaces we have come up with is the 2D scatter plots, the variability charts, the box plots, and the 3D scatter plots. You really need this dynamic exploration mechanism because that shows you the potential variables that can actually show the difference between, defective and non-defective parts. And you can clearly see where the defective parts are and where the non-defective parts are. That's the main reason for the graphical user interface. Okay, so now I want to focus our attention to the case study. This is a case where, and I picked this very interesting small case, is the total of 6 defective parts and were found at a specific downstream operation. And in this case, our customer in this case was Huawei. And what we did here is these 6 defective parts went through the same process of feature selection. And you can see we use the interactive data exploration and the learning tool that we had come up with. And here you're identifying out of the 1,600 variables we talked about, we identified the top 10 variables that we are studying. On the right side is an example of kind of the decision trees, the cart mechanisms we have used. But we've used all the 3. So you can see if you look at the decision trees, we have used the cart, the gradient boosting tree, and the random forest. And please note one thing is in each of these cases, variable 1 and 2, which basically the same variables are being unnumbered and are being studied. Variable 1 and 2 is common for all 3. But notice the third one, variable 10, here is variable 4, and here is variable 3. And we carefully study that just to see if there is something else that we are missing from the studies. And so you can see all 3 different decision trees showed variable 1 and 2, but the top 3 relevant, the third one is not common between them. So each one of them are picking different things. And using this, what we found is, I'm not specifically showing the details of the variables here, but you can see variable 1 and variable 2. Out of all the defective parts and the non-defective parts we have studied, remember we got 6 parts that returned from the customer. And the red one is the defective part. 0 is the blue is the non-defective parts. And you can see this methodology, you can show that 5 of them belong to this cluster. And the 6th one is here. We still did not figure out why this was causing the problem. But as soon as we saw this is very interesting because then you can have a very nice mechanism. You can go back to the process and actually figure out where it is happening and create this specific box to say anything around this box would be discarded and will not be shipped to the customers. And then you can avoid a ton of engineers working on these details. So the lower right quadrant is the defective units fall as outliers of correlation between variable 2 and 1. And by the way, I'm just only showing variable 1 and 2. This is not just a 2 variable study. It can be multivariate studies, right? And once you find this, then comes the next step is how do you make it part of the manufacturing step as a causal mechanism for corrective actions? So then the next discussion is, okay, I understand that this happened, but are there some other additional things that from the site, anything happened because of the site, anything happened because of the location of the parts, etc. So one interesting thing that we found was when we looked at these returns, those red ones, your returns are here, and most of the returned units were mostly distributed on the wafer edges. So that also told us that, depending on how serious this is, that we probably need either to figure out how to look at the wafer edges or even discard the wafer edges if we are having very strong difficulty to find out where the issues are coming from. So I think with this, I'll summarize the whole process that we have followed. It's take a unique processor ID. You are going through a whole lot of assembly process of the data, and then using feature selections and decision trees and machine learning. In this case, we have used supervised segmentation analysis and supervised machine learning. That's the output. In order for us to output that, we really need a dynamic graphical user interface. And once you take a look at the various sections of the graphical user interface, the differences between the defective and non-defective, you can start taking a look at the coming up with a corrective action plan or a monitoring mechanism so that you can actually make a change all the way in the test so that future designs, future processes don't have that problem. So with this, you can really save valuable time on investigation, deliver the results faster. You can do a lot of user interactivity with the data and the results, and you can start studying the problem from various different angles, which is not possible by following the regular methodologies. And once you are able to find this type of correlations, you can deliver a lot of intelligence on the causal mechanisms of defective parts. And the more important thing you can do is impact the decisions on the subsequent units. And then also, as you manage the customers, one of the other things you have to do is for the parts that you have delivered, what do you do? For the parts that will go from now on, what do you do? So you have two-step plan for that to manage the customers. So I think with that, I will end. Thank you very much. And I'll take any questions from here. Ramana, the floor is yours.
So thank you, Rahima. Actually, we are running late, so I'm going to apologize to the audience for not answering these questions live. I have the set of questions, and if they are not coming, if they're coming with a name, I will be able to pass them on to you and cover them offline. So thank you, Rahima.
I want to once again thank our sponsors who have made this event possible, our premier sponsor, Kohu, our emeritus sponsor, JonsTech, our honored sponsors, ISC, iWind, and TSC, our distinguished sponsors, Backer Hotwatt, Innovative Circuits Engineering, JMT, Nidec SVTCL, R&D Altanova, and UI Green, and our exhibitor sponsors, ELES, MJC, Phoenix Test Arrays, and Smiths Interconnect. So when you have a chance, please thank these companies for sponsoring, which has made this event possible and has made it available free of charge. And once again, I would like to thank Kohu, our premier sponsor, the market leader in test interface solutions for the most challenging applications, and ISC, the global #1 total test solution provider. So we thank them both for their leadership. And once again, I thank everybody for attending, and we look forward to seeing you again tomorrow at 7 a.m. Pacific. Thank you.